thanks organizers for the opportunity to have a talk here. I'm here in Novosibirsk for the first time. It's a pleasure to have a presentation on this conference. So I will tell you about an approach for approximate optimal controlling of mobile robot with a trailer. Consider a mobile robot with a trailer on a plane without obstacles. The position both robot and trailer has one pair of wheels. And the position of the robot is given by the midpoint of its wheels and the orientation of the robot with respect to the axis X. And the position of the trailer is given by the angle phi with respect to the orientation of the robot. And the problem is to move a mobile robot with a trailer from one configuration to another configuration. And since such problem has continuum solutions, we introduce cost functional to minimize and to choose optimal control among the whole family. So we can formulate the following optimal control problem. Q represents point in configuration space. We have a linear on controls differential system, which is defined by vector fields x1, x2, boundary conditions, and Subramanian lengths to minimize. Here we have no bounds on controls, but we can. This problem actually is equivalent to the problem where we assume that controls lie on unit circle, and we should minimize time. So this problem is equivalent to this time minimization problem. In fact, I formulate here not one problem, but the family of problems, two-parametric family, because here we have two constants, LR, LT. Let me tell you, I skipped this part, that those constants, they define distances between midpoints of wheels and connection point. And those constants, they define the model of our mobile robot with a trailer. So for each value of values of LR and LT, define Subramanian problem. And it seems very challenging task to solve such a family of problem, because as you could see in previous talk, even one problem is hard to solve. So the aim of my work is to find approximate solutions for this problem. So in such situation, usually linear approximation is used, but since we have, but for this control system, linearization is not controllable, since we have the dimension of control is less than dimension of configuration space. So we cannot use linearization, and the right approximation in this case is Nilpotent approximation, which preserves this important property of the system. So to construct Nilpotent approximation, we have to consider the following control system, which is also linear on controls, and this system defined by Nilpotent algebra. This algebra defined by this table and commutators of vector fields, they vanish at some step. And this is simplest structure of algebra in this situation, and by if we consider Taylor extension of these vector fields in privileged coordinates, we can obtain the following vector fields. So this problem, left invariant Subramanian problem on the angle group, is nilpotent, and it gives a nilpotent approximation in terms of optimal control with respect to this integral post-functional. And now I will tell you how to solve this problem and how to use the solutions of this problem to the initial control problem, which I told you before. So optimal controls existed because of Filipov's theorem, and we can apply Pontryagin maximum principle. Since we have no strictly abnormal curves, let's go directly to the normal case. Optimal controls defined by maximum condition, and Hamiltonian system has the following form. Notice that vertical subsystem is reduced to pendulum equation, and the behavior of pendulum defines behavior of our trajectories. So in simplest case, system is integrated easily, and we have straight lines, circles, and critical elastic. Note that projection along x, y are area elastic. All extremal trajectories are expressed by this family of curves. This family appears in the classical earlier problem, where we have elastic rod with length 1, and we hold this rod at the ends, and we need to find which configuration we obtain for given boundary conditions, so for points and directions at these points. So this is classical problem, and solutions are Euler elastica, and in this problem Euler elastica also gives us optimal trajectories. So in general case we have two types of trajectories. Inflectional elastica, you can see here examples of those elastica, and I can say that here in the limit we have straight line, so we start from straight line, then it became something like this, and then at some moment we have a special figure of 8. You can see it here, and then such type of elastic. So how those elastic are parameterized. So there is a parameter k which defines form of elastic. So for k belongs from 0 to 1. So if k is 0, we have straight line. If k is k0, which is this value, we have figure of 8, and in the limit, when k is equal 1, we have critical elastic. So also we can start elastic from any point of elastic. So for instance here, if we shift, we can obtain the same elastica but started from this point. And here you can see that we have this subfamily of elastica which have the same form but they have different phases. So there is a phase parameter, and there is also parameter alpha which stretch our elastic. So we have three parameters, and parameter time t gives us 4 dimension, and this mapping from 4 dimension to 4 dimension is called exponential mapping, and it's defined also for non-inflectional elastica. It's elastica which don't have inflectional points. So here you can see that all elastic have inflectional points. So here, and those curves, they don't have inflectional points, and you can see they have this form, and in the limit you can see that they're going to the circles. So we construct exponential mapping which gives us all extremal trajectories, and as I said, this exponential mapping it has continuous symmetry, stretching. So later I will use this symmetry in my investigation. So now we have extremal trajectories, and we should find the time where those curves lose their optimality. So at some moment we should cut elastica, each of them, and find this moment where it loses global optimality. So how to do it? We should find the Maxwell points. Maxwell point is a point where we have two different elastica. For these points we have two different elastica which goes to this point, and those elastica, they have the same lengths. So after this point those curves are not optimal. So natural way to find those Maxwell points is to consider discrete symmetries. So discrete symmetries in our problem, we have 8 discrete symmetries, and they appear from reflections of pendulum, and then we continue them to the image and to the pre-image of exponential mapping, and we have to consider fixed points of those symmetries in the image and in the pre-image, and fixed points in the image means that we have the same endpoint, and fixed points in the pre-image means that we have that symmetry doesn't change trajectory. So it means that after the symmetry this trajectory coincides. So in the pre-image points should not be fixed, so we can obtain two different trajectories. So in the end we obtain Maxwell time, and now we have upper bound for GACT time. So we know that after Maxwell time the trajectory is not optimal. So how to prove that this Maxwell time gives us exact point of when we lose optimality? First, we should investigate conjugate points, and we have to consider Jacobian of exponential mapping. And it appears that this Jacobian is quadratic function, but coefficients are very complex, because exponential mapping in general cases is given by Jacobi elliptic functions and elliptic integrals of first and second kind. So this was done with help of computer algebraic system Mathematica, and we proved that Jacobian doesn't vanish on some areas in the preimage and in the image of exponential mapping. So we obtain this estimation for the Maxwell time. We proved that conjugate time is greater than Maxwell time, and then we proved that domains which cut out by Maxwell time in the preimage and in the image, the exponential mapping on those domains is diffeomorphism. So we proved that before Maxwell time, if we consider this point for the on the extremal curve, we know that to this point we only one optimal curve is going. So for these conditions, when we have that when they are not zero, we have unique solution. So if they are zero, it's other situation, and we studied this situation now. And but for numerical computation, we can go out from this surface just to, for instance, if x1 is equal 0, we can consider x1 equal plus minus epsilon, and solve two problems with this boundary condition. So this is not a problem. And finally, we obtained the expression for the cut time, which coincides with Maxwell time. And those four theorems were proved with my supervisor Yuri Sachkov. Now we can use this result to find optimal solution for the angle group, and in order to do it, we have to invert exponential mapping on subdomains. But in order to do it, we have to. Okay. So here is the family of all optimal elastica. You can see that inflectional ones before 8 they lose optimality when x equals 0, and after 8 they lose optimality when area is equal 0, and this is meaning of third coordinate z. So, and non-inflectional elastica, they lose optimality also at when x equals 0. So here you can see whole family of optimal curves, and the movie is this movie, each picture of this movie corresponds to the special to the value of phi, to the value of phase. So you can see the form of elastica remains, but we attach in the initial point this elastic at different place. So now, now we, in order to find optimal curves for our problem, we have to write some program which numerically can calculate optimal solutions, since it is impossible to invert exponential mapping because of its complexity. So I wrote algorithm also in program system of Mathematica. It uses standard methods like Newton method, second method of random search, and concatenations of those methods. They form a new method which I developed during this investigation, and this method it found the optimal solution for my problem. So how we can apply the solution for the problem of on the angle group to the initial problem? So we have to calculate brackets, and then we obtain matrix gamma, which gives us transformation from one coordinates to another. And then then we found the coordinates for the problem on the angle group, found the solutions, found optimal controls, and then plug those controls into the initial system, and then integrate the system in numerically. And I consider special case of this problem when we have to repark trailer. When a robot should stay at the same point, we have those boundary conditions, and we have to repark trailer from one angle to another. So corresponding point for the problem on the angle group has this form, and actually it corresponds to the figure of 8. So we have to use these solutions, and these solutions are given by these optimal controls. So and also I should mention here that there is a symmetry where we can, so when we consider mobile robot and the trailer, we can choose the scale. So we have no scale on our plane, and choosing the scale gives us this symmetry, because we can change the distances of LR and T, and so distances x and y also changes, and we change parameter u, and it gives us other integral, more general, where we have here coefficient mu, and we can choose any mu. And this mu, coefficient mu, gives us balance between angles on the plane and linear distances. So here you can see here you can see movie for reparking trailer. We have to repark trailer to this shadow position, and the algorithm which I developed solves this problem quite fine, with almost no mistake, errors. So here are other example with other type of connection. You can see that trailer is attached in the midpoint of the robot, and you can see that the accuracy is quite fine, and is not the difference is not visible by human eye. So also we have here is example when we have the same distances, and we have part from this position to this position of the trailer. And again we have nice accuracy. And also I wrote program for parking robot and the trailer where the point is arbitrary for the robot. But here we have, since it's approximate solutions, we cannot guarantee exact solutions. And there are also problems like you can see here when robot touch this this segment, and in reality when we have this situation it brings us problem because you cannot so in this model we can rotate trailer as we can do, like around and around the robot. But in real robotic systems, we have limits for the angle feed. So this should be solved in the future, and it will be done for the improvement of the algorithm. And also I should say that sometimes the solution is close, but the difference is very visible. You can see that here in this example robot and trailer parked nearby, but still we have the same, the angles is quite fine. So we consider parking problem for mobile robot with a trailer, and it appears that Subramanian problem on the angle group gives us a Nilpotent approximation for this problem. And optimal solutions for Nilpotent problem are area elastica. We obtained cut time along pitch of extremal trajectory. And then we reduce our problem to solve to the system of algebraic equations, and we we construct algorithm and program which solve our problem, and then applied it to parking problem. And future for plans, we plan to study a symmetrical case when we have x1, xz equals 0, not use this trick, but choose exact solutions on these surfaces. And there is also, as I said, some gaps in the algorithm of Nilpotent approximations, because sometimes we come not with desired accuracy. So this accuracy should be increased. And in the end, we plan to apply this algorithm for controlling a real robot. Here you can see picture of here is only one robot, but you can see that we have already developed the attaching, the connection system. Here here is this connection point, and we also have a trailer. So now we start to see what trajectories a real robot shows us with this optimal control. Thank you for your time.
Questions?
So my question was Andrei group. Is it true that abnormal geodesic there are two and
No.
parameterized by arc lengths, and both are
are not strictly abnormal. There are normal which covers those abnormal, and I can show you that.
And the tangent defined, so for any such case, there is special basis such that the tangent vector do not commute only with one vector of basis.
Yes.
Yes, thank you. I understand.
I can show you that the abnormal trajectories are vertical lines here. So one is going up and another going down.
Other questions? I would like to ask. So you demonstrated that when you take approximate, when your system is not true, but just original system is not important. When original system is not important, sometimes you do not have a good matching. Okay? And did you try to iterate simply?
Yes, actually
It helps or not?
there is such an approach to iterate, but I don't like it because it gives us extra maneuvers. In fact, what I missed in my talk that I improved this algorithm in other way, not by iteration, but so for instance, we have this initial point, and we have to come to this point. This is desired, and nilpotent approximation gives us, for instance, this trajectory, and we come not with accuracy which we need. So my proposal is not to calculate nilpotent approximation at this point, but calculate it earlier, here in the beginning. So we come some segment, let's say some value t tilde, and at this point we calculate nilpotent approximation. In fact, we can calculate at each point on the way and see the family of trajectories and choose the one which is closer. And we can iterate this again with the same trajectories. But here sometimes this also doesn't give us the accuracy which we need. But I think all I have to do is just construct this algorithm more in more systematic way, because I think sometimes you can consider not one family but two parametric family of curves and choose among them. So here is still space for improvement of this algorithm, but I don't like this iterative because sometimes we come very close, and in order to come to this close point, we have to do such behavior, and this is not optimal. This is not really optimal at all. So I want to avoid such situations.
You have two free-fall distribution, yes?
Yeah.
After nilpotentization, and you have two parameters, LR and L of the trailer.
Yes.
And is there some special ratio of these two parameters when your program is have some big group of symmetries? For example, like in rolling balls program, where you know when you have two radii and when one of them is third.
Yes. Actually, I did not study in detail this original system, but I should tell you that there is special parameters LR, LT when they equal, and actually this problem loses controllability property at this point when phi is equal to pi. So when we have robot and it appears that trailer, so these distances are equal, and if we move trailer here, trailer and robot coincide, and you can get away from this situation. So here you should somehow avoid this value of pi, but in real robotics anyways we avoid this position. So, but about symmetric cases, I don't know, should study the problem, I mean should study this original control system and I did not.
Other questions?